Welcome back. Today we're going to cover chapter 4, which is kinematics in 2 dimensions, and then we'll finally be done with kinematics. And not really done because we're going to talk about Newton's laws, which is why do we have acceleration in the first place? To begin with, we explain how acceleration came. So in kinematics, you don't ask the question of where did the acceleration came from or what caused the acceleration. You just say, here is an acceleration, use it to tell me what the position and velocity and so on for the subject is, or for the object is. In dynamics, when we do Newton's laws, then we will talk about the cause of the acceleration, which is the force. You're given forces, you use the forces in Newton's laws to find the acceleration, then you use the acceleration in combination with your knowledge of kinematics to predict the position and velocity and so on of the object at later times. So the focus of today will be motion in, or kinematics in 2 dimensions in general first, and then we'll talk about projectile motion, and then we'll talk about circular motion. So projectile motion is a special case of kinematics in 2 dimensions where there is acceleration only in the y direction, meaning downward, and there is no acceleration in the x direction because there is only gravity in the downward direction. And then for circular motion, it's a special case also because it's motion where, in fact, we're going to talk about uniform circular motion, meaning the speed is constant. You're going around a circle at constant speed. And so the speed is constant, and also your distance away from the center of the circle is also constant. And so let's begin this. So in general, for an object that is in space, I will draw it in, because we're talking about 2 dimensions here. It could be 3, easily generalized. So here is the x-axis, here is the y-axis. We first have to draw our coordinates. And then let's say our object was here, right, initially. And then it follows a certain path. A little later, maybe it's here, and then here, and then here. So let's say our object, we follow it, and this is the curve it follows, just a general curve. And so here is, maybe it started like that, all right? So here's the position of our object at time t, and this is the location. We will draw a vector from the origin to here. This tells us the location with respect to this origin of the object. This is called r. This is r. So this is r. A vector r at time t. And this is the x component of the vector r. This is rx. And this is the y component of the vector r. So in fact, so we can write our vector r of t, as an x component called rx plus a y component called ry. And then it's in the j hat. Remember, I hat means x direction, j hat means y direction. And the x component of r, we can call it x as a function of time, I hat plus y as a function of time, j hat, all right? So that's the location of the object. The object, though, is moving. So at time t, the object is here. A little later, the object is here, right? And this is the location of our object a little later. Let me draw it in orange here. This is the location of the object at time t. Not at time t, but a little bit later, at time t plus maybe 1 second or 2 seconds, plus delta t, or at time t plus delta t. So this is here, this is x at time t, and this is x at time t plus delta t. Similarly here, this is y at time t, and this is y at time t plus delta t plus delta t. So that's rt. So let me write it here. R at t plus delta t will equal to the x component of r at t plus delta t, and we call that, let me just put my equal sign here. It's at x at t plus delta t I hat plus y at t plus delta t j hat. Why am I bothering for doing this? Well, I would like to find the speed or the velocity and then the speed of motion. So how do I find the velocity? How do I define the velocity of the object? Well, the velocity of the object would be the change in position divided by the change in time. So the velocity, as usual, we can define it as the change in position, which we call delta r, the change in position, over delta t. What is the change in position? Well, the change in position is the final position minus the initial position. Oh, I'm sorry, this is the average velocity. If I want the instantaneous velocity, I have to put the limit as delta t goes to 0. Let me put it here. I'll just rewrite this. So it's the limit as delta t goes to 0 of delta r over delta t. And what is delta r? It's the final position, which is r at t plus delta t minus the initial position, which is r at time t divided by delta t. Okay, divided by delta t. And so delta r itself is a vector, because a vector minus a vector will give you another vector. Remember when we introduced vectors, we said a vector space is the space that contains the set of all vectors. So you can take a vector, you multiply it by another, by a scalar. You can take the difference between vectors, they all fall back into that vector space. We say it's closed under addition and scalar multiplication, meaning the sum of two vectors is still a vector. The difference between two vectors is still a vector. Anyways, so how does this, first of all, how does this vector delta r look like? It's the final minus the initial. You have a vector that looks like this minus this vector. So how do I draw it? I just want to give you a visual. Well, delta r, in fact, will look like this. Let me use red. Delta r will be this vector. Would be a vector that points from here to here. So this one. This is delta r. Why is that? Well, let me just show you why. I draw the vectors by themselves. This is, let me call this one here R2, R later, and this is R initial, R1. So here is R2, and R1 looks like this. How do I do R2 minus R1? Well, R2 minus R1 is R2. How do I draw minus R1? Well, minus R1 would be a vector that's in the opposite direction to this one. And so if I add these two vectors together, this minus R plus R2, that will give me a vector that looks like this. And so, in other words, delta R is R2 minus R1. That means R2 will equal to R1 plus delta R. R1 plus delta R. I just move this to the other side. So if you have R1 plus delta R will look like this. Remember how you add vectors? You take the first vector, tail to tip, and then take the second vector, put the tail of that second vector at the tip of the first vector and draw it straight. And that will be the sum of the two vectors. That's why delta R, I know it looks like that. Anyways, that was maybe besides the point, but I just wanted to make it clear. Fine. So now, what is R at t plus delta t? R at t plus delta t is this. X at t plus delta t I hat, y at t plus delta t j hat. And R at t is x of t I hat plus y of t j hat. So how do we subtract them? Remember, when you subtract vectors or add vectors, you add components together. You add the x's, the ones in the x direction together and the ones in the y direction together. So it will be, the difference between these two vectors will be x at t plus delta t minus x at t, both of them I hat. So it will look like this. And I forget my limit sign, limit as delta t goes to 0. So it will look like this. It will be the limit as delta t goes to 0 of x at t plus delta t minus x at t I hat minus y at t plus delta t minus, plus y at t plus delta t minus y at t j hat, the whole thing divided by delta t. And so we can, the limit of a sum is the sum of the two limits. And so this becomes the limit as delta t goes to 0 of x at t plus delta t minus x at t divided by delta t, and I hat plus the limit as delta t goes to 0 of y at t plus delta t minus y at t divided by delta t, j hat, don't forget the j hat. And so by definition, this is the derivative of x of t. So this becomes dx dt I hat plus dy dt j hat. So this is the x component of velocity, I hat, plus the y component of velocity, j hat. And so this is what we mean. The limit of delta r over delta t is dr dt. So this is what we mean by dr. So in other words, if you have a vector r, how do you take the derivative of that vector? Simply take derivative of the x component with respect to time plus the derivative of the y component with respect to time. That gives you the velocity. Okay, and that's it. So let me just show you an example. You might get lost in the math steps, or they come in the way. Let's just do a quick example here. Here is the example. Here is r of t. The position of an object is given by this function. It's given by 2t minus 3t squared I hat plus 3t squared minus 4t cubed j hat. All right. And so the question is, question A, find x of t and y of t. Well, this is the same as x of t I hat plus y of t j hat. Okay, so that means x of t is equal to 2t minus 3t squared, and y of t will equal to 3t squared minus 4t cubed. All right, that's A. Let's do B. Part B. Let us find the position at time t. What's the position at t equal to, let's say, 1 second. What is the position at t equal to 1 second? Well, r at 1 second will equal to, just take the position and plug in 1 second everywhere. So it'll be something I hat. Let's plug in 1 here. So 2 times 1 is 2 minus 3 times 1 squared is 3, and then plus 3 times 1 squared is also 3, and then minus 4 times 1 squared is 4, j hat. And so r at 1 will be what? Negative 1 I hat and negative 1 j hat. Sometimes people usually, nobody writes it like this. Everybody would write it as negative I hat, negative j hat. All right? That's the position. What's the magnitude of the position? R at 1. The magnitude. We simply write it as R at 1. It would be the x component squared plus the y component squared. So it's square root of that. So it would be minus 1 squared plus minus 1 squared. And that's equal to the square root of 2, which is 1.41 approximately. Okay. Next, we're going to ask, let's see, find the velocity as a function of time. All the velocity as a function of time would be dr dt, and we just have to take the derivative of the vector r with respect to time. Let's do it quick. So I would have I hat, and then, by the way, I hat is a constant vector. It's a vector that points in the x direction and does not change direction. When we do polar coordinates, you will have vectors that change direction and they're not constant. I hat and j hat in Cartesian coordinate, they're constant. So let's take the derivative of this. Meaning this is just a constant. You can view it as a constant. What's the derivative of 2t? That's 2. And the derivative of negative 3t squared, that's minus 6t, I hat, plus, what's the derivative of 3t squared? That's 6t. And then the derivative of minus 4t cubed is minus 12t squared, minus 12t squared. That's the velocity as a function of time. That's the velocity as a function of time. Let's do d. What is the velocity at t equal to 1 second? Well, we plug in 1 second here, and you get 2 minus 6 times 1 is 6, I hat, plus 6 times 1 is 6, minus 12 times 1 squared is 12, so minus 12, j hat, and that gives 2 minus 6 is minus 4, so that's minus 4 I hat. And then 6 minus 12 is minus 6 j hat. Okay. What's the magnitude of the velocity? At 1 second. At 1 second, the magnitude of the velocity is just, you take the x component and you square it. So minus 4 squared. Plus you take the y component and you square it. Minus 6 squared. And you do it. 4 squared is 16, and 6 squared is 36. So 16 plus 36 square root. And how much is that? That's what? 46, 52, practical. Square root of 52, and it's in meters per second, assuming everything is in SI units. At what angle? Well, let's find the angle. First of all, how does the velocity look like? It's minus 4 units in the x direction, minus 6 units in the y direction, so it looks like this. The velocity is 1, 2, 3, 4 units in this direction, and then 1, 2, 3, 4, 5, 6 units in this direction. And that's the velocity vector at 2 seconds. V at 2 seconds. I'm sorry, at 1 second, not at 2 seconds. At 1 second. That's V at 1 second. So I'm asking, let's find this angle here. All the tangent of this angle here, I'm going to call it theta. The tangent of the angle will be the opposite over the adjacent. And I will just work with absolute values. I want to find theta. So theta will be tangent inverse of the y over the x. So just the absolute value of both. So it's minus 6 over minus 4. And what do we get? We get, better be more than 45 degrees, right? You see, slightly biased toward the y, so it's more open, so it's more than 45. And I get 56.3 degrees approximately, 56.3 degrees. And as I explained before, that gives you just this angle. You are to make what you will with it. You have to, the calculator will just give you a number. It doesn't know that it's in the third quadrant or the first quadrant. And so you're supposed to say 56.3 degrees below the negative x-axis, right? This is the negative x-axis. Or you can say it is what, 180 plus 56. You can also say it this way. What is this angle? It's 180 plus 56. 180 plus 50 is 230, so it's 236.3, approximately 236.3. Let me just add 180 just to not say the wrong thing. Yeah, it's 236.3 degrees from the positive x-axis. We can say it that way. If you like, you can say it's 56.3 degrees south of west. Also, that's another way to say it. Some people might want to use this angle and say, what is minus? This angle here would be 33.6, so you can say it's 33.6 degrees west of south. That's also another way to say it. Anyways, there are a variety of ways. Or just draw a picture with this vector, this angle, and say that's the angle. That's the 56.3 degrees. All right? And so now we'll talk about the acceleration. Okay, so how do we define the acceleration? How do we define acceleration? Well, velocity was dr dt, so the acceleration would be dv dt. dv dt. So let me, I will keep this board here because I want to refer to this problem. I want to refer to this problem in a moment. And I will use the whiteboard here. The acceleration will be a vector, it's A, and it will be dv dt. So remember, r of t was equal to x times t I hat plus y, the position in the y direction, times t j hat. So the velocity, you take the derivative of this, so it will be the dx dt I hat plus dy dt j hat. This is also known as the x component of velocity I hat plus the y component of velocity j hat. The acceleration will equal to dv dt. Oh, I'm sorry. The acceleration will be dv dt, and we have to take the derivative of this with respect to it, because this is v, and we have to take the derivative. So you take the derivative of this with respect to time, so you get the second derivative of the position in the x direction, dt squared I hat, plus the second derivative in the y direction, dt squared j hat, plus, that's it. And this part here is known as the x component of acceleration, I hat, and this part here is the y component of acceleration, j hat. So, in the spirit of our previous problem, we had r of t. Let me just pull it. I forgot what it said. R of t was 2t minus 3t squared I hat, 2t minus 3t squared. 2t minus 3t squared I hat plus, so 2t minus 3t squared I hat plus 3t squared minus 4t cubed. 3t squared minus 4t cubed. 3t squared minus 4t cubed j hat. And we said we said v of t was the derivative of this, so that's 2 minus 6t I hat plus the derivative of this one would be 6t minus 12t squared j hat. And then the acceleration as a function of time would be the derivative of the velocity with respect to time. Derivative of 2 with respect to t is 0, it's a constant. And then derivative of minus 6t with respect to t would be just minus 6. That's it. We'll just have the I hat. And then plus, here you have derivative of 6t with respect to t is 6. And then the derivative of minus 12t squared would be minus 24t and then j hat. And if I ask you, what's the acceleration at t equal to 1 second? You plug in 1. In the x direction, it's just minus 6 I hat. It doesn't change. It's independent of time. And then in the y direction, it will be what? 6 minus 24t, 24 times 1. So 6 minus 24 is negative 18. So minus 18, minus 18 j hat. Minus 18 j hat. And that's it. This part here is known as ax, that's the x component of acceleration, and this part here is the y component of acceleration. Okay, okay. So now, what if you're given the acceleration and it's and you want to know what the velocity is as a function of time? You want to work backward. Instead of being given the position, you're given the acceleration and asked to work backward. So what do you do? And that's what I would like to just show you next. So in the next video, I'm going to introduce motion at constant acceleration, and we will talk about how to work backward.